Okay, so I wanted to make a recording here for the week 10 lecture, and hear that? I got the boom mic too close, and that's my mustache rubbing on the mic. So if you hear that, I'm sorry. So we're going to talk a little bit about satellite systems, and basically what we're going to talk about first is how they fall into three categories: coarse, moderate, and fine resolutions. And this has to do with instantaneous field of view, or how big of an area we're looking at on the ground at any one moment. So first, let's look at some of the coarse resolution satellites. The TIROS is a television and infrared observation satellite. This was launched in 1960. So this is a very coarse, very old satellite system. Let's look at some of the other systems that are out there. For example, here is one, GOES Imager. This imager has various instrument characteristics, and we'll go over this because this is kind of the basic stuff. Every satellite has some area or some range of properties that it measures and that kind of stuff. So this particular satellite has 5 bands. Band 1 is in the visible range, 2 is in the shortwave, 3 is up in the range affected by moisture, 4 is in an infrared band, and 5 is a second infrared band. These specific wavelengths you can see listed in the table below: 0.5 to 0.75, 3.8 to 4, 6.5 to 7, 1020 to 1120, 1150 to 1250. Not only do these different sensors or bands collect in different ranges, they also have different instantaneous fields of view. And the radiometric calibration for this is space and 290 Kelvin infrared internal blackbody. And the calibration frequency is 2.2 seconds. And for the infrared, it's typically about 30 minutes. The system absolute accuracy is infrared channel less than or equal to 1K, visible channel 5% of the maximum screen irradiance, imaging rate 4th disk less than or equal to 26 minutes. It's also rapid scans for small areas. So this is the kind of information that you can find about these individual satellites that might help you decide which one you need. The AVHRR is the Advanced Very High Resolution Radiometer. This is a polar orbiting satellite, and you can see how it collects images, and then you have to sort of put them together to make them fit to get something like you see there at the bottom, which is kind of that unpeeled orange peel, if you will. This whole process is made up of different satellites at different times, TIROS, and a bunch of NOAA satellites as well, and the dates that they were in service. And as you see, some, like NOAA 10, are still up there, and others, like 11 and 12, have been decommissioned. So let's talk about some of the AVHRR bands, and we're going to look at them based on the different groups of satellites. And so the NOAA 6, 8, and 10 versus the NOAA 7, 9, 11, 12, 14, and 15. You can see that each of these satellites only collect in 5 bands, but where those bands are changes. Let's talk a little bit about MODIS, the Moderate Resolution Imaging Spectrometer. This is the sensor that is aboard the Terra EOS-AM and aquatic satellites, the EOS-PM. And it collects a total of 36 bands, and the reason it does so is because it is designed to allow for imaging of land, ocean color, clouds, ozone, temperature in the land, the oceans, and the clouds, as well as water vapor and aerosol. And to do this, you need a lot of different data. Yeah, and you can see some information here about its orbit and how it works, and the type of satellite, type of sensor, cross track, and all that. And then you can see the spatial resolution of the individual bands, 250, 500, 1000, depending on which one, and it was designed to last 6 years. So here's some of that MODIS imagery from the Terra satellites over the left coast of the US around about October 26th of 2003. At that time there were 3 rather large fires around the San Diego, Los Angeles area. Actually it's more than 3. And here you can see in this imagery where the fires are burning. The DMSP is the Defense Meteorological Satellite Program, and it basically shows you a lot of stuff. Particularly one useful thing is global lights at night. If you're trying to look for areas that are uninhabited or lack physical infrastructure that would be similar to power grids and lighting, you can see that there are large areas in certain parts of the world where it just gets dark, and that's a good thing in some cases. So you're probably wondering, well, what's the big deal about all these satellites that we keep talking about? There are a lot of them. Some of them are still in service and some are not. So some of the information that you might want is available. Some might not be available during the time that you want because they may have been decommissioned or they may have stopped working. What you need to do is figure out which satellite collects information that you need in the time range that you need it. And then that is the satellite that you need to focus on learning how to download data from. The SPOT VGT, it's a lot like the AVHRR. It has blue, red, near-infrared, mid-infrared bands, 1 through 4. Actually, I guess it's 0, 2, 3, and 4. It has a 1,000 meter instantaneous field of view for some things, and 2,000 instantaneous or 2,000 kilometer field of view for others. When we move up to the moderate resolution satellites like SPOT HVR, SPOT is an acronym for Système pour d'Observation de la Terre. That's my best poorly Frenchy sounding accent because I can't speak any foreign languages. I can barely handle English. But basically it's the system for observing the Earth. And this particular satellite was put up by a group of people, a group of countries rather, French, Belgium, Sweden, and Italy all went together, and it's a combination of private and governmental entities. And it's on a near polar orbit, 26-day revisit cycle. So if you get an image on one day, the next day that you'll be able to get that image to that same location is going to be 26 days away. And so that's one of the other things you have to think about when selecting a satellite for remote sensing is you might not be able to get satellite or even multispectral or any kind of imagery on the day that you want, at the time that you want. And so you may be shopping for a window of before and after, not necessarily finding a specific day. SPOT HVR, it's a push broom, lots of detectors. It's pointable, so you can aim it a little bit. And I'm sure that comes with a fee. It has more frequent visits near the poles than it has between track stereo. The SPOT HVR data is panchromatic and multispectral. And you can see here, depending on which SPOT satellite you're on, or which bands, what you might get. The IRS is not just a horrible taxing arm of the federal government, it's also the Indian remote sensing satellite, and there is various data that it collects as well. Another common satellite we come across is Aster. This particular sensor is flown on the EOS Terra, and this satellite is Japanese in origin. 14 bands of information it collects, and some are at 15 meters, like the green, the red, and the near infrared. Others are at 30, like the 6 different shortwave infrared, mid-infrareds that they collect, and some are at 90 meter, like the 5 thermal bands that they collect. And it has backward stereo, whatever that means. And here's what some Aster imagery can look like. Now, if you're looking for some really fine resolution stuff, following the demise of the former Soviet Union, a lot of prior collected high-resolution aerial photography was declassified, and a lot of that has become available, and you can get quite good imagery from all around the world from Russia. Iconis is another system. It was first launched in sometime before 1999, and it did not work. When they say it did not work or it failed, that means that it blew up either on launch or it failed to function once in orbit. Either way, it was millions and millions of dollars that they got nothing out of. But Iconis 2 was launched in 1999. It is a precise orbital tracking registration. It is pointable. It has a 3 to 4 day revisit. Collects a lot of information. Has 4 meter multispectral imagery. So if we were to look at what Iconis data can look like, here is the city of San Francisco viewed from the Iconis satellite. QuickBird is another popular one, launched in 2001. It is very similar. Has a 0.61 meter panchromatic and a 2.4 meter multispectral data collection capacity. Similarly, there is the WorldView satellites. These were launched by an outfit called Digital Globe. Has a panchromatic sensor at half a meter, 1.7 day revisit time, and it can be pointed as well. So if we were to go down the list and think about what you need in terms of resolution, whether it's coarse, moderate, or fine, this list sort of tells you what they all are. Now let's talk about one of the largest sort of groups of satellites that we deal with on a routine basis, and that is the Landsat satellites. So let's chronologically go over the launch and retirement history of these satellites. Landsat 1 was launched about 1972, so it literally is as old as I am. 74, 75, second one went up, third one went up around 78, Landsat 4 about 82, 5 went up around 84, 6 around 94, and 7 ultimately around 98. Now if we go back over the list, you can see that Landsat 1 only lasted for 6 years. Landsat 2 went from 75 to 83. Landsat 3 was up there from 78 to 83. Landsat 4, it started in 1982 and is still collecting data. Or at least it was at the time of this slide back in 2000. So it's likely not probably still doing that. Same with Landsat 5. Landsat 6 was a failure. When they say did not achieve orbit, that means the rocket blew up. Landsat 7 was launched in April on tax day in 1999. So let's look at how these satellites have changed a little bit over time. We go back to the first 3 Landsats. They had these big solar arrays to collect things. They had various sensors and scanners, and they had the multispectral scanner, the MSS, along with various other cameras and things that they needed, and ways of controlling their position in space. Now, in order to maintain a sun-synchronous orbit, it has to rotate around the Earth at a specific rate and time, so that when it gets back to that same location after a certain number of passes, it's at the same time of day. And just to give you some context, the individual path width of the satellite at the equator is about 159 kilometers. Middle part of the U.S., it's only about 185 kilometers. For example, if you look here in this image on the right, you see the black and the gray arrows. The gray arrow is orbit 1 on day 1. The black arrow is orbit 15, and that's on day 2. And then orbit 2, day 1, and orbit 16, day 2. And so you can see that it's about 15 days out till it comes back to getting close to the same spot. And so this is what the orbital track looks like, and you're wondering, how can you fly something in an S-shaped curve? You don't. You're flying it in a straight up and down loop around the globe, but the planet is turning at the same time, and that causes it to do and very much look like this. If we compare the components of Landsat multispectral scanners from Landsat 1 through 5, let's see what we got. What is the multispectral scanner? It is a scanner. It is in the satellite, and it is a whisk broom scanner. In other words, it travels from side to side, and it collects 6 lines simultaneously for each mirror sweep. If you look at a Landsat full image, you see it's about 185 kilometers square, but it's not square, if you know what I mean. It's sort of twisted a bit, and that's because of the rotation of the Earth. What bands does Landsat's multispectral scanner collect? Well, bands 4, 5, 6, and 7 collect 5 to 6, 6 to 7, 7 to 8, and then from about 8 to about 1.1. What is the ground resolution? It changes a little bit. When we get up to satellites 4 and 5, still has the multispectral scanner, but it also has the TM, or the thematic mapper, added to it. So the thematic mapper is a little bit different. We'll kind of go over what some of these things do. The thematic mapper collects a lot more information, and so it has different bands than what the other sensors did. So overall, if we look at satellites 1 through 7 in Landsat, and we look at the range of what we can see, you can see on band 1, it's blue and green. Band 2 is green. Band 3 is red. Band 4 is near infrared. 5 is shortwave infrared. 6 is thermal. And 7 is an additional shortwave band. The ETM Plus is 0.5 to 0.9 panchromatic as well. So what are the wavelength sensitivities of these selected sensors? If we look at spot 4, spots 1, 2, 3, the ETM, the thematic mapper, the multispectral scanner, you can see exactly what it is that they're collecting and where, based on this diagram. Landsat 7, newer satellite. here is one of the things that often gets overlooked. As the satellite's moving along and it's sweeping from side to side, the Earth is moving, you don't necessarily get continuous tracks. You see here how as you go along in one direction, the spacecraft is moving in another direction. And then you go back across and it causes the drift to change, and then it changes and it changes and it changes. And if you look at the various fields of view, it fills in fairly nicely, but it doesn't necessarily give you as clean an image as what you might think. Item C. To get it to look like that, when in reality it's collected like A at the top, requires a lot of work, and in the form of something called a scan line corrector, and where it stitches those things together and straightens them out. There's also this idea of a path row system. Each path has a number, like 16, 17, or 18. It's the various paths around the planet. And then rows are simply across the way at like 32, 33, or 34. All you need to do is figure out where you are on the path row system, and you know which information you need to download. For example, certain counties in West Virginia, you might want to be on 1733. 32 is too far north. 34 is too far south. 18 is too far west. 16 is too far east. But 1733 will catch it. Those paths are repeated. It's just going to be several days between times when it's there. Now, we've also talked about in the past how these sensors have the ability to detect information and how certain things create problems and interference in the spectrum. One of those things is clouds. For some wavelengths and some sensors it's not an issue, but for others they are catastrophic. And so if, for example, you just want to look at panchromatic stuff and look at the actual, true color imagery, you can't see through the clouds. This map shows you the percent probability of less than 10% cloud cover on a given day. And as you see, some places it's pretty good, others it's very, very bad. When the satellites went up, what they're capable of collecting, what sensors they have on board, and their orbital intervals. This is useful when trying to select a specific Landsat satellite, for example. We're going to talk a little bit now about the LiDAR side of things, elevation data, elevation information, how we create it, how we generate it. We've got some terms, DEM, DSM, NDSM, DTED, and DTM. Elevation model, surface model, and others. Terrain models, terrain elevation data. They're all similar sorts of things. What matters is understanding the difference when you're looking for the information. When we talk about how we measure elevation, we basically have three pretty common techniques. Photogrammetry, which is an indirect measurement. It utilizes parallax. Remember we talked about that, how something looks like it's in different spots on different photos when it's in the same spot. And we can use that change in apparent geometry from two overlapping images to infer height and whatnot. They call it a mature technology, which just basically means it's old. It's also relatively cheap to acquire, and it works. Then there's LiDAR data, which is a direct measure. There is no fortification of mathematics and the use of shadows and misshapings and distortions to figure things out. LiDAR is a direct measure. You zap a laser, it bounces back, you time it, and then you know how far away something is from where you're at. And if you know your exact position, then you know the exact position of the thing that you bounced the signal from. It's relatively quickly, but it has a lot of post-processing needs because it collects a ton of information, a lot of which is not terribly useful. But you can do it leaf off or leaf on, depending on the type of LiDAR that you're doing and the thickness and density of the vegetation. You can come up with some pretty amazing stuff. Then there's IFSAR, which is an interferometric radar. This is the fastest method of all. The problem is IFSAR does not like vegetation, and so it cannot sort of penetrate like regular LiDAR. What is LiDAR? Light detection and ranging is an acronym. The underlying principle is you're measuring the time on a pulse of light, and you know the speed of light, so if you know the time, you know the distance. Some places, like in Europe, they call it airborne laser scanning, or airborne laser mapping, or laser altimetry. And if you're not sure what laser is light amplified by stimulated emissions of radiation. Another acronym. It is basically an intense, narrow, coherent beam of light in a single wavelength. And this is what all the fuss is about. This is basically a type of a LiDAR system. There's a couple things you need to make it work. You need precise measurements of the angle of the laser detection. So you need sort of a gyroscope and a gimbal to control some of that kind of stuff. You need to know the exact location of the laser with a highly accurate differential GPS system. You need an INS, which is an inertial navigation system, which can tell the direction that the aircraft is pointing, flying, how it's pitching, how it's yawing, how it's towing up or down, and all that. Because all that combined allows you to identify exactly where you're at and the exact direction the laser is pointing, so that when you have the time of the return, you then know exactly how far away the object was that it hit. Scanning kind of works like this: flying at some altitude, traveling at some speed, zapping down on the ground, and sort of a zigzag pattern. It's sending down signals and picking up returns. I'm going to take a drink of coffee, and then we're going to talk about the history of it. Ooh. Lasers, developed about 1958. First used to measure long distances, like to the moon, in 1964 by leaving a mirror there that we could then shoot with a laser and measure how long it took for the signal to get back, and all of a sudden then we knew exactly how far away the moon was. By the 80s we had laser profilers. By the 90s we had laser scanners. There's a lot of commercial firms that do this, and the adoption of the technology has been rapid. Back in 1995 there was only about 3 systems that were available. By the year 2000 there were over 58, and there were 20 new ones that came out just in the year 2000. We have 2 basic systems. One is geared specifically toward land and doesn't work anywhere else very well, and the other one is has the ability to work in water to some extent. Infrared LiDAR doesn't get many returns over water because water has a tendency to, as you recall, absorb infrared. There is also a LiDAR that uses a blue-green type laser, which is not absorbed by the water, and so it penetrates, and this is a lot dependent on how clear the water is, but in general 3 to 4 times the depth that you can see with the naked eye. So if it's crystal clear water and you can see down 20 feet, then this will measure down 60 to 80 feet of water, and if it hits something solid, you get a return, and from this you can develop some level of bathymetry of the bottom of the body of water that you're scanning across. So what are the characteristics? You can fly in clouds and overcast conditions, and you can even do this at night. You can do it from a fixed wing aircraft or a helicopter. You can fly leaf on or leaf off, where photogrammetry requires 2 separate views of the ground and is often doesn't work as well in really heavily vegetated areas. When we collect this information, we're collecting basically 3 things: an X, a Y, and a Z value for each return. And when we do that, we can put that information out into what we like to call a point cloud, which is a 3-dimensional mass of these points. Now from that you can actually learn a lot. Here is a slice through of one of those clouds, and from this you can see how you get all these points clustering around the bottom. That is your surface. You see a couple that are lower. Well, that means that either something has a hole there that it allows it to get down and measure, or something bounced off of something on the way down or the way up and made it appear to be further away than what it is. The other data points in the middle can sort of show you the density of the vegetation, and then near the top you can see the density of the foliage, because this is looking at trees across a landscape. And so excuse me, so the first return you get, that's going to be the very top of whatever it is you're looking at, or the surface. And the last returns are the furthest ones down. Those are the terrain, or the land underneath. There's different information about the stuff that you can ask and inquire about the size of the area that it's measuring, how frequently it pulses, the way the scanner works, and all that kind of stuff. You also might have to or want to know something about its accuracy. Generally you're looking at vertically 15 centimeters, horizontally somewhere between 10 and 100 depending on the particular tool you're using. And you can also not just get elevation but intensity. And there's different ways of measuring your return, discrete or full waveform. I mentioned about the first and last returns. Sometimes returns are referred to as echoes, and so this illustrates how that works. The scanner up there in the chopper sends down the laser, it hits something and bounces back up. So we have a reference echo, which is basically of nothing. The first echo is when we hit something. The second is when we hit something further down, and the third and the fourth and whatever. And the last one ultimately is the surface. When we do discrete return measurements, the first return is the digital surface model. That's the tops of vegetation, buildings, or ground. The last return may be the ground, but you have to filter it for things that are non-ground points. So if there's a building there, you're not going to be able to get information through the building, so you have to remove the building and then interpolate across the space. There is intermediate returns. This is often used in forestry to give some idea of how dense the trees are, or the size of the trees. And the number of returns are measured. If you measure a continuous signal, you're usually looking at a larger area, like 30 meters. Sometimes we'll call it a large footprint system, like SLICER or the Vegetation Canopy LiDAR mission, which was a NASA program that got canceled. And they do a really good job of representing the distribution of vegetation within the canopy. And so all that stuff in the middle, where it's a lot like noise if you're just trying to get a digital elevation model, you can actually learn quite a bit from it with some of these types of LiDAR systems. And so this just is an illustration of how that might work. Post-processing is a significant part of this type of information. The projection information that you need for the stuff is important. Any conversions you have to do, you have to interpolate from the data points to get the surfaces that you want. If you do manual post-processing, you gotta remove errors, things that aren't on the ground. So like if you have something that's above the ground like a bird or a tree, it's gotta go. If you have below the ground, a double bounce path, something got interfered with, they have to go. If you're looking at a terrain model and you've got a building, the building's got to go. There's lots of things that has to be taken care of. And while it's not cheap to have the equipment or to rent it or to have an aircraft and to fly it, the acquisition or the actual going out and collecting this information is only about 40% of the cost. 60% is the post-processing. So we have different classes of LiDAR data analysis. The generation of digital surface models is one. Bald Earth mapping is a digital elevation model. Digital Earth model, this is without vegetation or buildings, is another. We can use it for change detection and object identification. There's a lot of software out there that allows us to input these things in directly. CAD, and there's some power line softwares as well. And you can also use it for forest attribute measurements. These are all different classes of data analysis that we do with LiDAR. As far as the format of LiDAR and the software, well, the big problem is it's point-based, and most remote sensing software is raster-based. GIS software is often vector-based, but it's not set up for large data volumes, and so you have to work with all these little issues. And ultimately, you end up interpolating a digital elevation model. You lose some data. You might have multiple values for one cell, and other places you have none, and you have to interpolate from a larger area. So there's lots of things going on that can create problems. This is what measured LiDAR vegetation might look like. You can see when you do some of the processing how you get these various points that are on the ground. Some are the vegetation, some are the trees. We have different applications. Atmospheric LiDAR, which measures the degree of scattering related to the profile. So the composition, the temperature, the wind. Oceanographic stuff like depth and obstructions. And terrestrial things that measure a wide range of particularly powerful stuff for identifying like topography underneath vegetation. So here is a nice example of a canopy surface model where we have a reconstructed 3D figure of everything, trees and whatnot, and filtering through the LiDAR data to then only show the terrain underneath the surface. You see how there's a lot of detail that you may not see in the canopy model that shows up on the surface. Turns out this has made a lot of headlines in recent times in Central and South America, where they've scanned parts of the Amazon and other jungled regions in Central America. And what they've found is lost aspects of the civilization, temples and cities that have been reclaimed by vegetation, that are unseeable by the naked eye, that you can't find, that there's no longer roads to, and that no one knew still existed until they flew LiDAR and filtered it properly, and lo and behold, they found pyramids of, or not pyramids, but temples, Mayan temples and Aztec temples and Incan temples and whatever they are. And only by using this technology were they able to find some of this stuff. A lot of potential out there in forestry applications as well. Not only can you identify the tops of the trees to see how high they are, you can get some idea of how thick any undergrowth might be. So here we have a georeferenced or a registered point, if you will, that we know is the exact same tree. And we have LiDAR sets from 3 different time periods. And you can see where the top points were in 98 and 99 and 2003 to get some idea of how the tree is getting taller, and to some extent how the tree might be getting maybe a little bit wider. It's hard to say. But from this information alone, we can tell that it's 3 meters taller over that time period.